What can I say about Ramón?
No, come on.
It's difficult. So he is an expert in condensed matter theory. He started working in superlattice and quantum dots in presence of time-dependent potential.
Where is Gloria? She left.
And then he moved later to the Kondo physics in quantum dots. And then after the Kondo physics, he started looking for many body effects in transport, in nanostructures, in mesoscopic system, and also Coulomb blockade. And now, I think he's working mostly in hybrid system between semiconductor and superconductor, looking for this Majorana fermion of this Andreev possible qubits.
Mm-hmm.
Okay. He has an impressive list of publications, which has collected an impressive number of citations. So he's very smart. And I have to say that he has a lot of papers in collaboration with experimentalists. So that means that when the experimentalist has some good experimental result, which they are not able to understand completely, they look for Ramón. So, this is important. So we have in the institute a lot of theoreticians who collaborate with experimentalists. But the experimentalists are not at the institute. I don't know why. So probably the institute should try to bring experimentalists making interesting experiments. Besides the experiments they are doing now. Okay. It's okay? Okay.
Yeah, it's okay. I think we can start. Thank you, Luis, for the nice words, completely exaggerated words. And of course, thank you for the invitation to give the seminar. And also, Unai was the first actually asking me to give a seminar a few months ago. Actually, somehow it got delayed. But okay, I'm really happy to be here today and give you this talk. So the title of the talk you have seen already. This is From Majorana to Andreev and Back. And perhaps some alternative title would be novel qubits based on this hybrid semiconductor superconductor devices. And the plan of the talk would be more or less half of the talk. I will try to give you a kind of overview, kind of a very introductory overview with ideas, kind of almost outreach level. I will try. And then in the second, in quantum technologies and in general in quantum computing. And you know, you can ask yourself the question of why am I talking about these novel qubits? I mean, there's a huge progress in the field. There are these very, very important companies like Google, IBM, all these companies, a lot of money invested in quantum computing and in general in quantum technologies. So I think it's a valid question to ask why are we still studying other systems beyond this kind of mainstream approaches. And the truth is that for all qubits, and in particular for these winners these days are these superconducting qubits like IBM or Google, you know, they publish this kind of roadmaps and everything. But I think, although you see, if you are not in the field, you see this kind of roadmaps like, you know, almost 10 years from now, they already have plans for building big supercomputers based on qubits. As I said, this is superconducting qubits, but there are other technologies that I will mention very briefly. The truth is that we are still in this kind of setups these days. So this is an image from IBM. This is last year or 2 years ago. This is a typical lab where you see a dilution fridge. This is without the cover. You have here two researchers. And you know, inside this kind of dilution fridge, you will have some qubit device, like you know, some circuit, in this particular case a superconducting circuit. Perhaps you have something a bit more advanced, but at the end of the day, what you have here is a chip with a few qubits, perhaps around 100 qubits or so, in a large facility, which you know, you really need a lot of control on these kind of devices here inside the holder, inside this dilution fridge, very advanced electronics, very advanced labs. So I would claim that we are still in the kind of ENIAC era. So this is, if you compare this picture with this picture, I think we are still here. We are still in the ENIAC era of quantum computing. This is just before the transistor was invented. This is fully based on bulbs, as you all know. So, these companies and these important labs keep publishing data and publishing roadmaps, but we are still very, very far away, I think, from having a true universal quantum computer. And the main reason is that we are really far away from being able to control decoherence. In general, a qubit is a quantum two-level system. You have a strong decoherence, typically, and you need to make a lot of redundancy. This is the idea. So to fight for decoherence, for each logical unit, for each logical qubit, you need to make a lot of redundancy, meaning thousands of hundreds of thousands of qubits in a real quantum computer. While these days we are still, you don't see here, here, we are around hundreds of qubits. So we are really far away from having, thousands or even hundreds of thousands of qubits to have a true universal quantum computer. All right. So again, this is the image. This is now is Google. Again, this is a dilution fridge, and the idea is always the same, at least for a standard superconducting qubits or semiconducting qubits, which is the same. You have some circuit inside the fridge in which you are able to isolate a two-level system. This is the famous Bloch sphere. You have a two-level system, a quantum two-level system, and there are many ways of isolating a quantum two-level system. And what you want to do is to play with these quantum superpositions to make this, at least on paper, this very powerful quantum computing with this kind of quantum two-level systems. And as I said, the winners these days probably are superconducting chips, but of course there are other platforms. So like here, if you Google it, you will see many, many companies and many, many platforms for quantum computing. Starting from superconducting, you have also trapped ions, you have photonic qubits, Rydberg atoms, neutral atoms, very, very promising platform, the Rydberg atom, and semiconducting qubits, silicon spin qubits in semiconducting chips. This is also very promising because, the semiconductor industry is very powerful, and there's a really advanced technology behind chips that we carry in our pockets, in our mobile phones. So this is very promising. And there are other companies like Microsoft which are trying to demonstrate another kind of qubits which are called topological qubits. All right, so what is a topological qubit? So, these days you go to ChatGPT and you ask, what is a topological qubit? I would like to know about topological quantum computing. And actually the answer you get is pretty good from ChatGPT. There are many, many aspects of topological qubits that you can read if you want, if you Google it, if you ask for it in your computer. But the point I want to make here is this fault tolerance and scalability. The idea is that these qubits, at least on paper, are less susceptible to errors, to decoherence, and hence this need of huge scalability would be less drastic. This is kind of the idea behind these topological qubits. All right, so what is a topological qubit? You all know this is well, maybe not all of you, but essentially this is in some mathematical language, this is an empty state, and this is an operator that creates an electron out of this empty state. All right? This is the kind of language that we usually use every day for our equations. Don't worry, I won't discuss many equations today. So in a kind of cartoon manner, this is the idea. So you take an empty glass, you apply some operator, and you have a filled glass. And the empty and the full glass are my qubit states. But this would be like a standard qubit where full or empty belong to the same glass, essentially. The idea of these topological qubits, of these Majoranas, is that I want to halve the glass in two halves and then separate each of them very far away from each other. So these two halves of the glass are the Majoranas, okay? So you take one electron, which is my full or empty glass, I halve it, and I have two glasses very far away from each other, and they together form a fermion. But this is an extremely non-local entity. This is extremely non-local fermion. And the idea is that the coherence is typically some local environment to this half glass. So this is here. This is the idea. Noise and decoherence are not allowed to drink half glasses of wine because it's a local noise source, typically. A fluctuation in your circuit, a charge trap, a flux fluctuation in your circuit, whatever thing, typically is a local perturbation which is not allowed to drink this half glass. Only very, very strong perturbations that can somehow see the full glass can lead to decoherence. So I found this funny cartoon in internet. This is a global decoherence. A huge glass that you can drink. This is a very, just to illustrate, a very strong global perturbation in your circuit is the only one able to destroy your non-local degree of freedom, your half glass. All right, so these are my Majorana states. My Majorana states are these half fermions that live at the boundaries of some material, and I will explain how to achieve this in real experiments. But for now on, this is a cartoon. So I'm able to split an electron in two halves. And this single electron that lives in two halves can be empty or filled. And this is my qubit, essentially. These are my two units that I use. My 0 and 1 are my two possible states of this fermion, empty or filled, which, again, are completely separate from each other. So this non-local nature is what makes my excitation protected. This is achieved in a superconductor. So ideally, these two excitations that live at zero energy, and hence the name Majorana zero mode, because this Majorana actually is an excitation living at zero energy in my material, is separated from the rest of excitations by a superconducting gap that we usually call topological gap. So this, at least in simple models, is what allows me to isolate a non-local degree of freedom, which is very robust against local noise, from the rest of excitations in my material. And these 0 and 1 are the basis of the qubit. All right, but I mentioned Microsoft. They are actually putting a lot of money, a lot of investment on these qubits. And again, a valid question would be whether these such exotic qubits already exist. You can go to Google, or you can see many news actually about Microsoft research, and they actually have this kind of chip that they call Majorana 1, and they claim that they have the basic blocks for such qubits, and they have already demonstrated this physics needed to build scalable topological qubits. So do such exotic qubits already exist? Well, I think it depends who you ask. In my opinion, not quite, but okay, perhaps this is, you can discuss about it. So they exist in some manner. So, this is a bottle that I have in my office. So this is the Majorana 1 chip that you can, I have one, but this is a cartoon in a bottle. And this is just a joke, but they actually have permeated in the US mostly. And you can see in videos in YouTube like this. This is a Senate hearing in the US Senate. This is Senator Ted Cruz holding one of the chips. It's Majorana 1 chip. And this is from a video in YouTube claiming that this is a 1 billion chip that the US have been able to create, blah, 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 and we are now in the frontier of research for qubits because we are able to have such topological qubits. So, they claim to have this, but I'm not sure. So this is at the level of politics. they even made it to TV shows. So this is a Charlie Big Potato. This was suggested actually by Luis. This is from a TV show called The Iris Affair, which is interesting. You can hear. So here you have the Majorana computer according to this TV show.
Potatoes.
Why?
Well, it's all small potatoes.
No, the noise is not very good,
It's
the
just a
sound.
name.
No, it's not that. You're diminishing it because it frightens you.
Yeah, it does a bit.
So what exactly is it?
What exactly is it?
It's a topological quantum device operating at very close to room temperature.
What is it used for qubits?
Majorana zero-mode quasiparticle.
Oh, Majorana zero quasiparticles in a TV show.
Configuration of
Electrons that can't suffer
Can suffer random error. So, you know, they made it quite okay.
And what about
Okay, but this is of course science fiction. Yeah, this is just a TV show. Actually, they have they combine this with organic materials, with neuromorphic. This is a completely funny thing. Anyway, this was a joke. But you know, so somehow it's many people actually at the level of these TV shows believe that these computers are existing at this level, but we are very far away from this thing. All right, in the talk, I will focus on how to make these things happen, at least the basic units. And what we have is something very exotic called a P-wave topological superconductor. This is similar to a topological insulator that some of you may know about topological insulators. So this is like the superconducting counterpart of a topological insulator. It's called a topological superconductor. And the edge modes of such topological superconductor are these Majorana modes. There are many, many theory papers back from more than 25 years ago that already predicted these exotic Majorana modes in models. And there are actually some experimental implementations very close to a P-wave superconductor. The most basic model is this, what we call a key-type chain that I'm not going to explain, but essentially the idea is that you have a chain, spinless, without any spin. You can have hopping between the sides, electron hopping, this is T, or you can have superconducting pairing, like Cooper pair-like pairing, but between sides. Instead of having Cooper pairs with different spins, what you have is Cooper pair pairing between neighboring sides with a delta. So this model predicts that when delta equals T, you have these half electrons, these Majorana zero modes, appearing at the end of the chain. This is kind of toy model, but actually you can prove that there are more advanced models, like models of semiconductors with a strong spin-orbit coupling, that when coupled to superconductors, develop this kind of behavior at low energies. And essentially, the idea is that you can create, inside the gap of the superconductor, you can create kind of a Dirac cone. And many of you have seen Dirac cones many times in graphene talks, in topological insulator talks. So the idea essentially is that you can tune a Dirac cone with electron-hole symmetry coming from the superconductor, and this Dirac cone can become topological and can host these Majorana zero modes. And the idea is to, as I said, to combine the properties of a semiconductor with the properties of a superconductor, very importantly in the presence of spin-orbit fields. I don't have time to give you details. I have like this Physics Today paper with Leo, where this is kind of more outreach or a full review on it, and there are many, many papers about it. But the idea is like, you combine materials, and you have some kind of emergent low energy behavior that mimics or realizes novel states, like, again, as I said, like in topological insulators or similar. So this is like cooking, right? So you have different ingredients. You put them together, and you create something new. This is the idea of emergence, right? You put ingredients, you put them together, and you have something which is new. It's completely different from the isolated ingredients in a cooking recipe. So for us, this is the calamari, boccata de calamares, a calamari sandwich. And this is something we use very often we have a heterostructure. We have a heterostructure between a superconductor and a semiconductor, which at the atomic level, this is MBE, these are images of MBE samples. You can combine things like indium arsenide or aluminum or indium antimonide. There are many combinations that you can create between semiconductors and superconductors at epitaxial level, at MBE level. And there are many growers in the world, well, not that many, but a few groups in the world that can create such clean interfaces between semiconductors and superconductors. All right, so again, the ingredients that you need are a strong spin-orbit coupling. This comes from the semiconductor. Large G factors, you want to break time reversal symmetry. You want to put large Zeeman fields without killing superconductivity. So this you can accomplish with large G factors. High mobilities of the semiconductor, gating tunability from the semiconductor, and all this combined with superconductivity can give you this kind of exotic states with Majoranas. All right, so a key concept in these devices is the concept of Andreev states, or subgap states in general. So the idea is that in a standard superconductor, you all know that you have a superconducting gap, but when you have gaps, or in general pairing terms that are spatially dependent, like in an S and S junction, you can create discrete levels inside the gap of the superconductor. And this is like quantum well levels, essentially. This is the discrete levels that you create in a quantum well. The only difference here is that you have this superconducting boundary here, and you have this, what we call an Andreev reflection. You are an electron that becomes a hole by putting a Cooper pair in the superconductor. And this creates superpositions between electrons and holes. These kind of discrete levels are, and this is important, superpositions between electron and holes in the superconductor that live inside the gap of the superconductor. And these are the Andreev levels. The Majorana zero mode is a very special case of these subgap states, when my discrete state lives at zero energy and is half electron, half hole. And this is when I have a Majorana zero mode. So a Majorana zero mode is a subgap level living inside a superconductor at zero energy. And this is the experimental signature that people try to measure. So essentially, by performing tunneling conductance experiments, you want to see how this gap closes. This is close to this Dirac point I was telling you about. And then you have this zero bias peak, which is telling you that you have a zero energy state inside the gap of the superconductor. So tunneling conductance against magnetic field are a signature, or at least this is what we thought a few years ago, are a signature of Majorana zero modes in these kind of systems. And the early experiments were published like in 2012, so more than 10 years ago already, claiming that these kind of peaks in tunneling conductance were due to these Majorana modes. This is from Delft. This is indium antimonide nanowire with a superconducting contact. And this tunneling conductance, this tiny peak was interpreted back then as Majorana zero mode. And there has been many, many other experiments, very advanced and state-of-the-art materials, state-of-the-art measurements, state-of-the-art everything. But still, there is this huge debate, and I'm sure many of you know about this Twitter. I mean, it's everywhere in social media. These controversies around whether Majoranas have been measured or not, whether Microsoft has these Majoranas or not, and there are some people still fighting a lot at the level of social media against this Majorana picture. And the point I want to make today is that actually the idea that Majoranas can be mimicked by other subgap levels is well known. I mean, we knew since, this is an email that I found from 2012. So, a few months after the first experiment, I was collaborating with Silvano and Edu. Some of you know Edu. Edu was a postdoc back then with Silvano. And, I was writing emails with them just right after the experiments, already interpreting this data as data coming from quantum dots. And this is the point I want to make. Quantum dots with superconductors can give you pretty much these signatures about Majorana zero modes. And there are many other mechanisms. Typically, these kind of junctions with superconductors can host subgap levels at very low energies, eventually at zero energy, that can mimic essentially all the properties of Majoranas. So we really don't understand this kind of noise in social media about these interpretations, because we understand this very well, actually. So, we actually wrote a review. This is El San Pablo with other co-workers, where we cover all the physical mechanisms. This is similar to the title today, from Andreev to Majorana. This is 2020 already, but we cover all the previous papers and discussions from the last 10 years or more. So we really understand what is going on with these kind of systems. So there is no such controversy in that sense. We understand these systems. There are subgap levels that can be at very low energies, that can mimic Majorana physics. And they are typically originated by quantum dot or similar physics in these kind of junctions. All right, so I made it to the half, yes. That's a very good question. Yes. So I wanted to discuss this at the end of the talk. That's an extremely good question. So every time you have a zero mode in a superconducting system with time reversal breaking, it is indeed a Majorana zero mode. You have even out degeneracies in the system, and I will explain this, and this zero mode is a Majorana. It's a different thing is whether this is a topological state, which is a completely different question. But when you have an even out degeneracy in a superconducting system, indeed, you have a Majorana zero mode. So these are kind of toy Majoranas, if you want, or non-topological Majoranas. All right, so this is half of the talk, so I'm doing well. So this was kind of the introduction to the topic. So what we want to do is a kind of change of paradigm. So instead of debating whether they are Majoranas, they are Andreev, blah blah blah. This is for people who like Twitter and social media and blah blah blah. What we want to actually use is that this knowledge we have gathered during the last 10 years or more about these systems. We really understand very well these systems. We want to use actually these Andreev levels to make or to design novel ideas, and in general to design novel qubits. So the talk, or the rest of the talk, would be combining this physics of Andreev and in general other subgap excitations in these kind of devices to design novel qubits. All right, so this is when a bit more technical part of the talk starts. First, I will briefly mention what is an Andreev spin qubit. So these days we are able to create a spin qubit, essentially, inside a superconducting circuit. This is an Andreev spin qubit. So taking the ideas from superconducting circuits like these IBM qubits or the Google qubits, we combine this with the ideas of the semiconducting qubits, the spin qubit. We put them together and we create what we call an Andreev spin qubit. And this is using, again, the physics of quantum dots. Then I will move on and describe very briefly some work in progress, what we call a gate-mon. But Edu is giving a talk in 2 weeks, so I will mostly skip the gate-mon because these are experiments from Edu's lab. This is a very nice collaboration. How to improve these Andreev spin qubits with what we call a Flaxonian geometry, and this is Jose Luis is here. I will mention this very briefly. And then hole-based systems. So instead of using electron like semiconductors, use hole semiconductors to try to improve these ideas. And then the last, hopefully the last 10 minutes or so, will be around this idea of the minimal key-type change. So back to Majoranas. So we were discussing a lot about Majoranas. We had all these controversies. We realized that quantum dots are there and can give you these subgap levels, these Andreev levels. We can manipulate these quantum dots to isolate degrees of freedom like this Andreev qubit, but now the next step is actually to use these quantum dots to come back to this toy model I was telling you about, this Kitaev model, and actually demonstrate that you can build in an experimental lab a Kitaev chain and demonstrate one of these minimal models for Majoranas. And this is what we call the minimal Kitaev chain. This is a Nature paper we published 2 weeks ago. All right, all these ideas and many others are in this review paper for physics report. It's in CONMAT. If you are interested in these hybrids, please have a look, where we cover all the ideas starting from standard superconducting circuits. All right, so many of you know the transmon qubit. This is a standard superconducting qubit, and actually I mentioned this in my talk about the Nobel Prize. This is essentially a Josephson-Janssen qubit, where you have an inductor which is slightly nonlinear. So essentially you have these levels coming from this inductor. When the inductive part, the Josephson coupling is much larger than the charging energy. You may remember this from my previous talk. This is what we call the transmon qubit. This is the basis of the Google and the IBM. A gatemon is when you replace the standard Josephson-Janssen by some S and S, where N is a semiconductor. So you can gate this semiconductor, you can tune the properties of the Josephson-Janssen by means of semiconducting elements. This is the idea of the gatemon. This is why it's called gatemon, gate-tunable transmon. So you can tune things like the critical current across this device, or even the qubit frequency by gates. But we want to go beyond that and actually use these subgap levels that I was describing a few minutes back. You can actually use these degrees of freedom, which are essentially fermionic degrees of freedom. They are essentially electron degrees of freedom. Sorry, my mobile. You can use these degrees of freedom to isolate a spin, well, I hope it doesn't sound again, a spin degree of freedom inside a quantum dot in this Josephson-Janssen. So we go from a standard Josephson-Janssen in a superconducting circuit to a semiconducting junction with a quantum dot. And we want to isolate a single spin degree of freedom in this quantum dot. The physics of this tiny object is actually quite involved. I'm not going to give you details, but Luis mentioned in this introduction, you typically have in a quantum dot, you have what we call Coulomb blockade. You have large charging energy, so you can isolate a spin degree of freedom. This is when the spin is coupled to a metal. And when you have a strong coupling between the spin and the metal, you have a condo. And Luis mentioned condo. You can have condo, a strong coupling between this spin and the electrons in the metal, forming these singlets. When you have a superconductor, the physics is very similar. But because you have this large gap, typically what you do is to quench this condo effect. But this famous, or maybe you have heard about the name Jussi-Varusinov state, a Jussi-Varusinov state is just a condo state. It's a condo state in a superconductor. This is what a Jussi-Varusinov state is. So you tune this kind of condo physics in this device, and you have this kind of phase diagram. This is the level position of the quantum dot. This is the coupling. And essentially, and I'm not going to give you details, the idea is that you can isolate regions in the system where you have a spin, or you can isolate regions when you have a singlet phase, which can be this kind of condo-like or Andreev-like solution. So spins are separated from Andreev levels or condo-like singlets by this kind of boundaries. And answering your question, every time you cross this boundary, you have a degeneracy between being a singlet or being a doublet, and along this line, you have a zero mode. So every time you cross this boundary as a function of parameters, you indeed have zero modes because you have even odd degeneracies. This you can prove experimentally, and these are experiments from Delft. This is Marta. Some of you know Marta Pita and Arno, who were PhD students in Delft. They did very nice experiments where they actually demonstrated this physics in a transmon circuit. So you have, a squid junction with two Josephson junctions. You have the capacitor, and you replace one of the junctions by one of these quantum dots. And this is my, simple-minded theorist, a cartoon. If you go to real life, the things are much more involved, of course. So this is the quantum dot. This is a nanowire, an indium arsenide nanowire with a tiny quantum dot. You have gates. You can tune essentially with these gates this phase diagram. You can put this in a loop, in a squid loop with another junction, and then put this loop in a circuit where you have, a resonator, a capacitor coupled into a resonator. So you do microwave readout of this circuit, of this very tiny quantum dot junction that leaves very small, tiny junction. This is a blow up here of this tiny region, and a blow up there, and there's a huge circuit behind. So this tiny junction actually governs the physics of this full circuit. And again, I'm not going to give you details. Essentially, the idea is that you can tune this circuit to have a single spin, believe me. Either with gate voltage or with flux, you can have what we call a doublet, which is a spin degree of freedom in the circuit. These are microwave lines. And actually, because you have a spin orbit, you can split these lines, and you have two well-defined spin branches in a superconducting circuit. So if you think about it, it's amazing. So you are able to isolate a spin qubit degree of freedom, which against phase, you can control the level separation between these two spin branches. And you, of course, can manipulate this as a qubit. And this was demonstrated in this experiment in Nature Physics. This is Marta was the first author. When they were able to, I contributed a bit with theory, they were able to demonstrate Rabi oscillations, coherent rotations of this spin qubit, and all things you want. Even a strong coupling between the qubit and the superconducting qubit. So you have two qubits, the spin qubit and the superconducting qubit. So this is just to illustrate that these circuits are very well advanced. They really know how to tune them. And you can indeed isolate a spin degree of freedom using the physics of these quantum dots with Kondo, blah, blah, blah. At the end of the day, you can really tune these systems to be a nice qubit. It is a nice qubit, but it's not the best qubit ever, because the decoherence of this qubit the decoherence properties are pretty bad. What we call T2 times, the dephasing times are rather short, are nanosecond times. So there are ideas of how to improve these spin qubits in superconductors. One of them, we know this comes from hyperfine interactions, from interactions with the nuclei in the indium arsenide. So one idea would be to get rid of nuclear spins and go to Hall spins in germanium. So there's a huge interest in the field to go to Hall semiconductors and to demonstrate a proximity effect with superconductors with Hall semiconductors, like germanium quantum wealth. We are doing something in these lines, and this is a very nice paper. Mitchell here is the first author, Jose Carlos, Ruben, and Maria Jose. We did the first actually full theory of this superconducting proximity effect in Hall-based hybrids, and this was actually an editor's suggestion in PRB. And actually today there is a paper in CONMAT where this is a nice collaboration with Yorgos Katsaros, which is a super nice experimental group in ISTA, in Vienna, near Vienna, where they have been able to demonstrate for the first time quantum dots with Hall properties with these superconductors. So what we call GRAL, granular aluminum. So if you are interested, this is just today, it appeared in CONMAT. So, but I'm not going to discuss this today because it's getting late. Let me just flash some ideas of how to improve this spin qubit. So you have two spin branches that actually, if you think about it, are phase dependent in the circuit. So by tuning with the phase in a squid, you can actually manipulate a spin degree of freedom in the circuit. So we were thinking about these ideas, and together with Alfredo and Francisco, Ruben and Jose Luis is leading these investigations. We were thinking about how to extend this idea and to be able to tune these phase properties of the spin by manipulating the circuit. So this is the standard circuit. So this is a Josephson junction, this is a quantum dot junction, and this is the squid loop. And what we want is to introduce an inductive element, like an inductor in the circuit, to be able to have extra phase tunability or flux tunability in the circuit. And this is what we call the IPA qubit, the inductively protective Andreev spin qubit. This is when we shunt this quantum dot junction by an inductor and we gain extra protection. This is our IPA qubit, which is a nice beer. This is actually the Olmo. Where is Jose Luis? The Olmo beer. I have found it. The Olmo beer, and you know, he's a crack. So it's everything there. So he's doing very, very nice calculations about this completely novel circuit, and I think I'm very excited about these ideas. And this is just to illustrate, these are the wave functions of the two spins living in a potential well with respect to phase, and how by tuning the properties, in this case by changing this inductor, we can separate spins in the circuit that live completely orthogonal to each other in phase space. So, of course, the overlap between these two spins becomes negligible when you tune them properly. And this is a contour plot of this integral. Well, it's not nice here, but anyway, this is the integral between the wave functions, and you see here that this overlap becomes essentially zero. So you can have two spins living in essentially orthogonal sectors of phase space. So you have a very nice qubit, and you can calculate T1 and T2 times of this IPA qubit, and it's very, very promising. All right, so I'm almost finished. As I said, this is another nice experiment with Edu. Edu is there in IFIMAC. Edu is actually, they are an associated unit with us, and they have been able to demonstrate for the first time one of these gate-mon qubits, one of these gate-tunable superconducting qubits, in what we call the ultra-strong coupling limit. When you go well beyond, for those of you who know a bit about quantum optics, you go well beyond the James-Cummings model. So you really need to incorporate counter-rotating terms in the light-matter interaction. You need to incorporate all these physics coming from these tiny levels I was telling you about these Andreev levels. You need to incorporate all the details of the Andreev levels and all the details about going beyond the James-Cummings model to actually fit the data pretty well. So this purple line is a theory line that Gorm calculated. But Edu, I'm sure Edu will tell you about it, but let me just flash these qubit results. So we have a qubit here on campus. So I think that it's the first fully made qubit in Spain, to be honest. Because, yeah, it's true. I mean, the other qubits are, they buy qubits, right? It's true. I mean, IBM, it's not the qubit you make, but this is I mean, Edu is very modest, but I keep telling him, you should stress this fact. I mean, you are the first person probably in Spain who has demonstrated a single qubit. So I think it's quite an accomplishment. Anyway, let me finish in the last 10 minutes by going beyond. I promised that I want to go beyond the single spin model. I have a tiny spin in this kind of circuit, and I describe how we can isolate a spin degrees of freedom, a spin qubit branches in a circuit. So the idea is now to extend this single dot, this single quantum dot idea to an array of, so this is my tiny quantum dot with the pepper, hot pepper. We want to extend this idea to an array of quantum dots, okay? And this is what we call the minimal key-type chain based on quantum dots. And this is actually the idea behind our Pathfinder project with Maria Jose and Rigid Goswami. Monica was here last week. Monica was a glorious student as well. And other friends, Yorgos is here, where we call this quantum bits with key-type transmons. So we want to extend this idea of the transmon superconducting circuit to incorporate these minimal key-type chains. All right? And instead of having a spin split lines, we want to have parity split lines. Remember that I was telling you at the beginning of the talk with this wine joke that 0 or 1 are the two possible parities of my state. My 0 and 1 are even or odd parities, but I want to use those non-local states to actually detect them in a transmon. This is the idea behind this Pathfinder. The full theory is in this paper by Mitchell, who is here. If you are interested, we can discuss about the theory. I'm not going to tell you anything about the theory. Also, Ruben was involved. Mitchell is an FPI student here, Severo Ochoa FPI in the Institute. All the details of the theory and quantum theory are in Mitchell's paper. Let me just again use kind of cartoon ideas to try to illustrate what a minimal key-type chain is. And this is Lego, okay? So what we want to do with these experiments is actually play Lego, okay? So we are going to have a superconducting block separated by two semiconducting blocks, which are the green blocks. This is my quantum dot 1, and this is my quantum dot 2, and in the middle, I have my superconducting bridge. This is what we call a minimal key-type chain. And believe me, there are people in the world that can create this experimentally, and I will show you images of this kind of minimal Lego key-type chain. And the idea now is simple, and this is following the key-type model I was explaining before. You can actually tune the system to have this kind of single electron hoppings across this superconducting block. And for this, you use actually Andreev levels. So Andreev levels are actually useful for having this single electron crossing all the way across my bridge. Or, this is very important, I can actually tune the system to break Cooper pairs in the superconductor and put one electron on each side of the Lego chain, okay? And this you can actually tune experimentally. You can tune a system in which this process delta is equally probable as the process T, as the process of single electrons, and you can have a well-defined Majorana zero mode. So have Majorana been discovered or measured, or whatever you want to put it? Yes, for sure. In these minimal key-type chains, there is a exquisite control on the properties of these tiny devices, and this is actually, again, an indium arsenide nanowire. This is quantum dot 1, this was my green block. This is quantum dot 2, this is my second green block, and this blue is the superconducting bridge. And indeed, they can tune the system to have this condition, and when this condition is met, when the single electron tunneling is equally probable to the Cooper pair splitting, you have a very clear peak at 0 voltage. When you don't reach this condition, you don't see this peak. So you can create at will Majorana zero modes in this minimal key-type chain. It is not a topological chain, answering your So good question. So this is a minimal chain. So this is one Majorana is here and one Majorana is there. Or in my sample, one Majorana would be in this boundary and another Majorana would be in this boundary. This is a very short chain. This is what we call minimal. But now there are other experiments. There is Rigid Goswami and Leo and others are extending the chain to have 4 sides, like a minimal qubit array would be 4 sides of such minimal key-type chains. So the nice thing about this is that you can actually scale this thing in a very, very controlled manner, because you have, like, this experiment is with a nanowire. There are other experiments demonstrating the same with 2-dimensional electron gases. So with 2-dimensional electron gases, Rigid Goswami, who is part of our consortium, is actually able to do the same kind of experiments with 2-dimensional gases. All right, so perhaps I should mention this. This is from Leo's group 2 years ago, precisely 2 years ago, where this is a very, very nice Nature paper where they demonstrated this key-type chain, which is no longer a toy model. In many talks, there are people saying, but this is a toy model for Majorana. It's no longer a toy model. I mean, there are experiments able to demonstrate this key-type chain block by block, like Lego. This is why I like this Lego picture. So let me skip this kind of a lot of theory behind this slide, but actually this is answering your question. So when you have even out degeneracies in the many-body spectrum of the chain, you can actually demonstrate that you have Majorana zero modes. Okay, if you are interested, we can discuss about the conditions. And the connection with the rest of the talk is that you can actually use Andreev bound states to mediate the coupling between the two distant Lego blocks with the middle superconducting bridge. This is a very simplified model. Of course, if you really want to understand all the details about the chains, you really need to put all the ingredients of this, you know, highly involved mesoscopic system. This is a mesoscopic segment with superconductivity coupled to quantum dots with a Coulomb blockade, charging energies, blah, blah, blah. So, you know, Miguel is also in the audience. Miguel Alvarado is doing very, very nice calculations. Ruben and Maria Jose are also involved, where he's really digging all the details about what we call the mesoscopic key-type chain. What is the role of these singlet doublet transitions in these mesoscopic chains, and how to extend the, actually, he's able to obtain analytical conditions, or when do we expect to have Majoranas in the chain, when we incorporate things like, you know, Zeeman fields, other spin degrees of freedom, coupling to reservoirs. I mean, he has done already very, very nice calculations on this kind of more realistic mesoscopic chains. So I'm finishing now. Let me just flash the idea behind our recent paper, our recent Nature paper. I was telling you at the beginning that with local probes you cannot distinguish the Majoranas, and I made the joke of this huge glass of wine. You really need to have something huge to detect these states. So this is kind of the idea behind this experiment. What we do is in this superconducting bridge, you couple this to a microwave circuit. You couple this to a slightly, you know, a small oscillatory signal, and the idea behind this, what we call quantum capacitance, is that the LC resonator, remember my talk about the Nobel Prize, the LC resonators in superconducting circuits, the LC circuit, which is a resonator, will acquire a tiny C component coming from this quantum system, and this is why we call it quantum capacitance. So essentially you oscillate the middle bridge, so it's like oscillating a bridge. Think about a bridge that oscillates coherently, and this way you can actually distinguish between being even or odd in the chain. This is the idea behind the experiment. You can do all the theory, blah, 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 but essentially the idea is that the curvature of these levels, whether you are even or odd, brown or blue, will have different curvature against this oscillation, and you can detect this curvature experimentally. This is the idea behind quantum capacitance. And Gorm did all the calculations. I mean, depending on the level of the model, I mean, behind this kind of plots, there is a lot of theory, because you really need to calculate how your system reacts to a microwave signal, in general in frequency space, and actually there are a lot of papers about this in general, because this is this is common in semiconducting circuits, and this is actually a very, very nice paper by Monica and Fernando González Salva, perhaps you know also Fernando, where they do this linear response theory of quantum electronic circuits. So essentially you do linear response theory, to make a long story short, including superconductivity, including these Andreev degrees of freedom, electron hole symmetries, and so on and so forth. And you know, you do the calculations, and Gorm was in charge of doing all the calculations. And this is actually quite involved. I mean, first time we discussed about these experiments was in Minneapolis, I remember, in the March meeting 2 years ago. And I was with Gorm, and we started discussing with Nick and Francesco. And you know, it was really involved in data until we actually understood the data. And I want to stress the fact that Gorm, who is a theorist, he was a postdoc with me, is equal contributor to this Nature paper. So coming back to Luis' comment, I mean, he's an equal contributor, a theory equal contributor to a highly advanced experimental paper, meaning that, you know, maybe theory is not that. I think it's a bit important in this kind of collaborations. So anyway, you are able to read out this kind of signals. This is how the microwave signal changes a bit by the presence of your quantum dot change, and you see these off-diagonal lines. This is microwave. You do a microwave experiment. You measure your LC resonator, and you see these tiny off-diagonals in the data that you can actually reconstruct by theory. This is theory from Gorm, where we understand very nicely these off-diagonal lines coming from this change of curvature of the even-odd branches, so we can distinguish the even-odd branches in this minimal key-type chain, or what we call the superconducting bridge. So by making a huge oscillation in the bridge, well, not that huge actually, huge for them, for this tiny structure, but for us it's not that huge, you can resolve the even or odd parity of the minimal chain. So indeed, you can resolve the parities in real time, which is amazing. So you can follow the trace of your microwave signal in real time, and you know, this is even, this is odd, and you know, from time to time you have some stochastic event. Of course, this system is not perfect. So the lifetime of this parity state is actually milliseconds, is above milliseconds. So this is very long lifetime for a qubit. So this is a very promising. We are very happy about this paper because this is very, very promising for a parity qubit, because this is millisecond lifetimes where you really see this kind of random telegraph noise signal. This is real-time data where you can resolve the parities very nicely, and the lifetime between stochastic events exceeds milliseconds, which is infinite for a qubit. It's very, very long lifetime. So next step is that they already have what they call the qubit sample. So they already have a sample with 4 quantum dots, with ideally flux control, and all the ingredients to demonstrate a minimal parity qubit based on Majoranas. So perhaps in this year, eventually they will publish data about this qubit, which is fully Majorana based. So have Majoranas been measured? Yes. Do we have a Majorana qubit based on parities? Not yet. This would be my answer. Okay, with this I'm done. I think I've mentioned everybody in the collaborations, but let me stress again Jose Luis and Mitchell, the PhD students, who have done all the important work. Also Miguel Alvarado and Gorm were crucial for these collaborations, and Jose Carlos, Ruben, and Maria Jose, and my collaborators outside the Institute in different experimental theory collaborations. And as I said, there is work in progress about these novel qubits, and I hope Edu will mention this Gatemon in 2 weeks here, so I'm looking forward to his talk. And again, you have details about these hybrids in this review. Thank you. Thank you, Luis.
Comment, question?
Or do I need to use the... Yes, because we are recording. Thank you for this nice talk. So, one question is, you said this is Majorana, but it's not topological Majorana. It's like a quark, but it's not a quark.
I mean, there is nothing. If you think about it, there is no obvious relation between topological physics and Majorana zero modes. I mean, Majorana zero mode, I mean, you know a lot of... let me reply with a slightly technical answer to Alberto, because he knows a lot about these things. You know, the Bogoliubov-de Gennes equation of a superconductor has this charge conjugation symmetry, essentially. So the BDG equation is already a Majorana equation, if you think about it. So at low energies, this Dirac equation with BDG symmetry in a superconductor with charge conjugation is a Majorana equation. So a zero mode in a superconductor, when you get rid of degeneracies, spin, blah, 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 it is indeed a Majorana mode and has nothing to do with topology whatsoever. The point about topology is that there are cases where you have edge modes which are protected, quote unquote protected, because samples are always finite. But at the extent of protection, like a topological insulator, you have edge modes which are well separated from the rest of excitations with a gap. And this is when you need to start about discussing about what is topological and what is not. And there is actually a very nice connection between this physics and the physics of these quote-unquote trivial modes, which is this physics of non-Hermitian systems. So when you put this in the language of... we have a very nice paper also with Elsa and Pablo and previous students, where we actually demonstrated that non-Hermitian exceptional point, you know a lot about this. You can actually make a connection between, you know, purely trivial in the sense of what Luis was asking me, even of degeneracies which are fully local to fully non-local topological degeneracies, in the sense of a smooth crossover. It's not a quantum phase transition. It's a smooth crossover where you go all the way from non-Hermitian exceptional points to Majorana zero modes in a bulk topological with invariants, all these things.
Okay.
I think Cefe had a question, no? Or no? Not anymore.
So I have a question. If the Majorana is not protected, is going to move from zero energy?
Yes, thank you for the question. So in these minimal key-type chains, this is what we call a sweet spot, and these Majoranas are called poor man's Majoranas, in the sense that you can change parameters in the system, and depending on how you change parameters, and there are many theory papers discussing these ideas, depending on how you move parameters, you move away from zero energy. So this is actually what Miguel is doing in this paper with the mesoscopic chain. So actually you need to keep track of three things. You need to keep track of to what extent your zero mode is a zero mode, but you also want to keep track of how localized is your zero mode. We use a quantity called Majorana polarization. And you also want to keep track of how far is this zero mode from the rest of excitations with the gap. So by optimizing these three variables, you find optimal fronts, optimal curves in parameter space when you can find that the three variables can be optimized or not. And this is actually what Miguel is doing now.
More question, comment?
So maybe two questions. You said that there's an analogy to the anomalous quantum Hall effect to Majoranas, which is just including now superconductivity. Is there any advantage to add this for maintaining the quantization, or it's like is there any more stability adding by the superconductivity, or is it just adding more noise?
There are many papers about this, using chiral superconductor, helical state, graphene, quantum Hall effect, anomalous quantum Hall, blah, blah, blah. And there are very nice theory papers, but the problem is always the same. Implementing this experimentally is super difficult. So there are some papers claiming to have some Majorana physics in some quantum Hall edges, things like this. But I wouldn't say.
And are they believed to be more stable? I mean, is it really worth going there?
I don't know. I mean, there are actually people like maybe Gleb Finkelstein, who is doing a lot of research on really using graphene, like chiral modes in graphene with superconductivity. He has super nice data on proximity effect with chiral modes in graphene, and you see extended Andreev states for I don't know how many Teslas. So these states are quite robust. Whether they are Majoranas or not, I think this is under discussion. But there are a few groups in the world trying these kind of ideas.
And maybe one last question. You said that there's the even odd parity conservation is very long, but this is not due to any topology or any topological protection.
Thank you.
So what is really the reason, or do you know the...
Right, thank you. This is also a bit technical, but you actually find this in the quantum dot experiment, in the single spin experiment. When you look at parity, when you look at the phase diagram of the Anderson model, maybe you recognize this dome as the Anderson model with superconductivity. This phase diagram with the Anderson model, you can do the same experiments. Actually, we were inspired by this experiment from Marta, and you can trace the microwave signal. And whether you are singlet or doublet in the single dot, is also the lifetime is super long also, and this is because of charging energy. You are using quantum dots to create your key-type chain, and you have a strong charging energy. So this prevents from having essentially quasi-particle poisoning. But it is true that you have a superconductor with a finite gap, and eventually you can have a quasi-particle entering the system, like in a standard superconducting qubit. You have from time to time you have quasi-particle events which are completely stochastic that spoil your state. But ideally, if you have a topological gap, quasi-particle events, and again there are many theory papers about it, would protect you, quote unquote, from random events. But I mean, in real life there is no topology. I mean, eventually.
So it's the charging energy.
It is at this level is the charging energy.
Any other question? So I have a question. It's about the blah, blah, blah. So it's, you are presenting some models which probably are sophisticated, but the input are some parameters. So the coupling between semiconductor and the superconductor, and maybe a lot of parameters, but the model in principle is easy to write, probably difficult to solve.
Okay, depends on the model, I would say.
But then you compare with experiments, and the agreement looks reasonable good. So my question is, how depends all this on the details?
Okay.
Because how it depends on how is in your arsenide, how the properties, what are the impurities, what is the distance between one thing and another.
Yeah, I understand the question. So thank you for the question. So this is where people like Gorm or Miguel are doing, can actually involve calculations. Mitchell also is doing a lot of calculations on this proximity effect with the whole gas, with quantum well, germanium quantum wells. So, when you tune this system, this is perhaps here. So, you use these Andreev bound states in the middle, in this blue Lego block, to tune the coupling between these quantum dots, right? This is a single electron is electron cotunneling, and the superconducting part is the what we call cross Andreev. But all the details you are asking for are here. I mean, you really need to consider that this is a semiconductor. Perhaps let me show the experimental image here. So this is a semiconducting segment like indium arsenide, proximatized by a tiny electrode, which is aluminium platinum in this experiment. So you really need to consider the proximity effect with between this superconductor and this semiconductor, and this is where all the details about the spin-orbit coupling, how strong this coupling is between the superconductor and the semiconductor, etc., etc. So all this governs the microscopic properties of these Andreev levels in the hybrid. And this is what I was calling the mesoscopic hybrid. So this is, for instance, what Miguel is doing. So depending on the degree of sophistication you want, and you can go very sophisticated in describing this mesoscopic segment, you can include the physics. You see here the title, singlet-doublet transition. So you can include all this physics of Kondo-like Jussi-Varusinov. You can include proximity effect from the very beginning. So you can take a superconductor coupled to a semiconductor by some tunneling term, and you can trace out the superconductor and obtain the effective coupling or the effective gap in the semiconductor. And if your model is difficult, like holes, like Mitchell now is fighting, he's almost hating me already, for obtaining this in a quantum dot with holes. You have the K.P models, all these Kohn-Luttinger model, you have heavy hole, light hole bands. So you couple this to a superconductor, you confine, you have Coulomb blockade, you can go very sophisticated to, at the end of the day, obtain the T and delta. But T and delta is not a number, it's something, I mean, you can put a number, but you really need to do microscopics before. Thank you.
Any other question, comment, remarks? Thank you very much.
Thank you.